So for the final part of this project/test, going to talk about Wigger's diagram and going to kind of explain how depolarization, pressure, and volume are, or what is really going on within the heart, all looking at it on one graph. Additionally, I'm going to talk about how atherosclerosis and some pharmacological drugs can affect this diagram. So there are 6 different steps of Wigger's diagram. The first step is atrial depolarization, which is our 30% active contraction. In this highlighted section that I have going on here, actually first I'm going to talk about the layout of this graph. We have our EKG or ECG, ventricular volume, ventricular pressure, atrial pressure, and aortic pressure. Now within this highlighted section, you'll see that atrial depolarization is occurring here. This is at our P wave and part of the QRS complex. So starting within the left and right atria, this is kind of where this is happening due to our P wave. And we're going to see an increase in ventricular volume because of that 30% active contraction. That blood is leaving the atria and entering into the ventricles, which is why we have a bit of an increase in ventricular volume, as well as it begins to plateau because that blood is all now within the ventricles. Then when looking at the pressure portion, we're going to see kind of this peak in ventricular pressure as well as atrial pressure. Ventricular pressure is going to increase because the volume of the ventricles is high, so it's going to put pressure on the ventricles. And that because the ventricles have a lot of volume in them, it's going to kind of push on the atria a bit, causing an increase in atrial pressure. Then aortic pressure is going to decrease because we have blood leaving the aorta because of previous steps, which we'll actually get to that in a second. Then we're going to look at step 2, which is isovolumetric contraction. This is kind of like the AV nodal delay going on here, and it's kind of at the end of the QRS complex where we've entered systole. And here we are still kind of in that plateau of ventricular volume because blood hasn't left the ventricles yet, because the AV node is still sending that signal down the left and right bundle branches up and out through the Purkinje fibers. So blood hasn't left the ventricles, which is why the volume is still the same. But we are going to see a bit of a rise in atrial pressure, and that is still due to pushing on the blood pushing on the atria. But we're going to see a huge spike in ventricular pressure because that blood is pushing up against our valves. And then we're also going to see still not much going on with aortic pressure, just because the blood isn't in the aorta, so there is no pressure pushing on it. Next, for step 3, we have rapid ejection. This is when blood is leaving the ventricles, and that's kind of going to be around the end of the QRS complex, more towards the T wave, and we're going to see a dip in ventricular volume because blood is leaving the ventricles, which makes sense. And then we're going to see atrial pressure kind of rise again because we're having blood return back to the heart from our veins. So blood is going to fill a bit in the atria, causing an increase in atrial pressure. We're also going to see still a rise in ventricular pressure because of the blood leaving the ventricles. We're also going to see quite a bit of a spike in aortic pressure because now we have blood in the aorta, putting pressure on the aorta. Next, we have reduced ejection, which is step 4. Now, this is kind of at the end of our EKG, or the T wave, sorry. And we're not going to have much blood in the ventricles, which is why we are at our lowest point within this graph for ventricular volume, because there's no blood in the ventricles. We've gotten it all out from our previous step. When looking at atrial pressure, it's slowly rising because blood is still entering into the atria, whereas ventricular pressure, it's kind of reached its peak and now it's starting to go down due to that contraction and the force exerted on the ventricles. We're going to have a bit of a downward peak in aortic pressure because blood is still in the aorta, but it's leaving to go to the rest of the body, so pressure begins to fall. Then, for step 5, we have isovolumetric relaxation, and this is when the aortic valves kind of close before the mitral valve is able to open. But in addition to this, the atria are full of blood, and so there's not really much blood within the ventricles right now, which is why ventricular volume is still plateaued at its lowest point. Then, when looking at atrial pressure, we're going to have a bit of an increase from this slope because blood is all within the atria putting pressure on the left and right atria. Additionally, when looking at ventricular pressure, it is still going down because there is nothing up against the walls of the ventricles because we have no blood within our ventricles. And additionally, aortic pressure kind of spikes a bit, and that is because of the atria. And then when looking at ventricular filling, we're going to see this is like our passive filling. So the valves finally open, and blood is now entering into the left and right ventricles, where this process kind of starts all over again. Oh, you'll have to forgive me. I am still sick and I have to cough. So give me a second. Okay, coffee saved the day. So just talked about ventricular volume. So, well, I mentioned that the atria, the valves opened, so that way blood could enter into the ventricles, so we'll see a spike in ventricular volume because of that blood finally entering into the ventricles. Ventricular pressure begins to increase and rise because of that blood entering into the ventricles, as well as atrial pressure starting to rise again because of the blood leaving the atria. It'll be pushed back onto the atria from the ventricles. And aortic pressure falls because there is not much blood hitting the walls of the aorta. So that is why there's a dip there. And that is Wigger's diagram. Pretty cool. A lot going on. Hopefully that made sense. Now, when looking at atherosclerosis, we're going to see that this is a huge inflammatory process. When the blood is constantly hitting up a certain place over and over and over again, inflammation is going to occur. And so at the impact site, inflammation begins, and this can release small, dense LDL, which actually kind of escapes. It doesn't release, it's just escaping. And so when small, dense LDL, or SD-LDL, is released, it goes through the intima, and they go by the adherence proteins. This then becomes oxidized, and when it gets oxidized, LDL protein becomes inflammatory in nature. This is not good because it agitates the intima. And so luckily we have white blood cells that start off as monocytes, and these monocytes kind of sniff around for areas of inflammation or even injury. And when they smell oxidized LDL, they migrate out of the blood and do their best to get rid of whatever is causing inflammation, which in this case is the LDL. So it leaves the blood and attacks the LDL, which is inside of the intima. And then, sorry, I have to drink my drink again. Once the monocyte is out of the blood, it becomes a macrophage. And so we know that macrophages pretty much are going to consume anything inflammatory, so the macrophages eat the oxidized LDL. The macrophage, then eats the oxidized LDL, and it becomes extremely large, or we'll just call it fat. So it is very large in fat, and it turns into a foam cell, which is fat trapped inside of immune cells. And this is what is causing expansion inside of the intima for atherosclerosis. And to kind of combat atherosclerosis, well, let's look at 3 inflammatory processes. We have COX-1, COX-2, and we have the 5-lipocurb. And so these are our 3 main processes for inflammation to happen, which the arachidonic acid sits inside of the cell membrane, and if it isn't activated, everything's okay, but in this case, it is activated, causing inflammation to occur within one of these 3 processes. And in order to combat the inflammation, we can use drugs. And so non-steroidal anti-inflammatory drugs can be used to block these pathways and to prevent inflammation. In addition to this, to kind of help with atherosclerosis, other medications can be used, and we want to kind of use things that wouldn't increase blood pressure. And I'll relate this back to Wigger's diagram in a second. So anything like a statin or calcium channel blockers or even beta blockers, anything that would cause the heart rate to be slowed down would allow for blood pressure to decrease, because we don't want to have an increase in blood pressure with atherosclerosis, because if we do have an increase in blood pressure, we're going to be putting more pressure on the arterial walls, and that is not good when we already have an inflammatory process occurring. So, when looking at Wigger's diagram, atherosclerosis is going to cause an increase in blood pressure. And if we have an increase in blood pressure, we're going to see an increase in atrial pressure, aortic pressure, and ventricular pressure. And so all of these pressure increases are not going to be beneficial for heart rate, for cardiac output, stroke volume, and ideally it is not something that you want to have occur because it could lead to other problems, such as heart attacks. So, when taking a medication to help with atherosclerosis and decrease our blood pressure, this will allow blood to efficiently get out of the heart without putting too much pressure on our arterial walls and ventricular walls, which is why we want to take these drugs to prevent increase in blood pressure.